Hello and welcome to today's SaferSim webinar. Today we are going to hear a presentation from researchers from the University of Massachusetts-Amherst. They are going to be talking about a microsimulation project that they did in regards to a SaferSim project. So with that, Eric, I will let you take over.
All right, thank you very much. So it'll just be me presenting today, but I've included Aaron Keegan's name here. He was a master's student who did most of the heavy lifting on this project. And what I want to talk about is a study we did using microsimulation to look at urban freight deliveries. And it started out really focused on looking at delays and capacity, and then we realized that our microsimulation tool allows us to also look at some safety implications by using surrogate safety measures. So I'm going to structure the talk today to talk a little bit about what we were trying to accomplish, how we went about building a microsimulation model, and then what we found both in terms of the delay and capacity effects of deliveries, but also the safety implications. So hopefully I can, okay. So, the main motivation of this is to understand, what can we do with information about where freight deliveries are happening? So this is a problem in a lot of urban networks, that not only are streets and cities moving people, but this is also how all the goods that we buy at stores or consume at restaurants get to where they are. And deliveries are often made by double parking, because the shippers don't have the time to go around looking for parking spaces that aren't available. And so they tend to, in dense urban areas, double park, blocking a lane of traffic while they load and unload, generally unloading goods. And we know that this has an effect on the capacity of the streets, but it hasn't been sort of systematically studied. And so that's what we wanted to do. We wanted to see if we could come up with a systematic understanding of how does the location and frequency of these stops affect the operations of traffic on these urban streets. And so, what can be done about it? There's been a lot of different approaches to try to incentivize shippers to travel at different times or go to different locations. The consequence, even though this is technically an illegal maneuver, is that most of these shippers are just passing on the costs of their fines to the people making the orders. It's just part of the cost of doing business. And so since it seems to be a problem that's not going away, we figured we would sort of address it head on and try to quantify it and understand if there's things that could be done to reduce the impacts, reduce the negative impacts on the delays that this poses on traffic, and also the potential implications for safety. So the way I've structured this talk today is just briefly talk a little bit about the other literature on urban freight deliveries, and also some of our observations looking at some real streets in Boston and New York City. And then there's three main parts. The first is efforts we made to develop an analytical model for what's going on, looking at the interactions of these vehicles and seeing if we could sort of, from a theoretical traffic flow theory perspective, develop a quantitative relationship between the location of the delivery and the impact that it has on traffic. Then we built a simulation model of this, and so we did a simulation study to compare with our analytical approach. And we use the simulation study also to conduct safety analysis using surrogate safety measures that I'll talk about. And then if there's interest, we also, just sort of because it seemed like an extension that was a low-hanging fruit and it was of interest to us, was looking at if traffic signals could be re-optimized, accounting for the presence of a delivery. So right now, because the deliveries are illegal, nobody reports that they're doing it. They just block the traffic and hope they don't get a ticket. But if we could detect that this was happening, is there something that we might do to change the signal timing to get better system performance, or recognizing that this is a reality on those streets? So first, to look at some of the literature. There have been a number of studies over the years looking at the effect of trucks, heavy vehicles in the traffic stream, and typically they focus on heavy vehicles in the moving vehicle stream. So we look at passenger car equivalents, so the effect of trucks is consuming some of the flow capacity on an arterial or on a highway. And this has been done through empirical measurements and also through simulation studies. There's been a lot less attention on the effect that these trucks have when they're stopped to make deliveries. One of the reasons is trucks don't usually stop on freeways or on suburban roadways to make deliveries, there's usually dedicated loading zones in suburban areas. But in urban street networks, the loading and unloading area is right there on the street, and it ends up resulting in a lot of double parking. And so a lot of the effort that's been put into this area has been either looking at this problem from the carrier's perspective, the truck driver's perspective, or the shippers, and trying to understand, how do they address the problem. It seems to be that for the most part, the truckers don't necessarily want to be double parking. They don't necessarily want to be traveling during the most congested times of the day either, but they do want to make deliveries at the times when their clients and their customers are demanding those deliveries to be made. And so whatever other extra costs come along with that is just part of the cost of doing business. And there's been a lot of research over the last decade to look at the potentials for off-hour delivery policies. The idea that maybe we don't want these trucks on the streets during rush hour or during the most crowded times of day. Could we move deliveries to lower capacity, times of the day when there's less traffic on the streets? There would be less impact. And the challenge with this is that requires, especially for deliveries to businesses, requires somebody to be at those businesses during the off hours. So you might say, well, the traffic flow would be smoother, there'd be less vehicle-to-vehicle interaction, so it'd be a safer, less congested experience to make these deliveries at night, for example. But most businesses are closed at night and the employees go home. So for somebody to have to come in after hours to receive a delivery, that costs extra money to the business as well. And so without sort of external incentives, this hasn't really taken off. There have also been some studies of the effect of freight vehicles on safety. But a lot of these have sort of looked at these things, like as a case study analysis, looking at particular locations or trying to quantify the issue in aggregate. There's not been a lot of quantitative systematic evaluation of how the freight vehicles stop on a street affects the traffic patterns and the sort of the details of where that freight delivery is made along a block and what that implies about vehicle-to-vehicle interactions. And the surrogate safety assessments that I've been able to find related to heavy vehicles have mostly been focused on simulations of urban freeways, not the urban street network themselves. Although the surrogate safety assessment model was developed particularly to be able to look at vehicle interactions at intersections. And so it seemed like an area where it was an opportunity to try something that hasn't been looked at very closely before. So there's a video here we have from a traffic camera in New York City, and it shows a very typical type of environment. This is 8th Avenue, and you can see that there's heavy traffic moving along the street and a large number of delivery vehicles, right? So in the foreground here is a mail truck delivering some mail. And the vehicles that are in that lane, most of their movement you can't really see because it's upstream of the camera, but they have to change lanes to get out of the way. And so that creates a bottleneck for flow, and that vehicles have to pinch down to get past that truck. But also the potential for a lot of vehicle interactions, lane change maneuvers, and rear end conflict that have safety implications. And this happens on every block up and down the street. But the locations of these deliveries is moving around. It's random. It's here temporarily. Once this mail truck moves, the blockage will be somewhere else. And you can see that there are various vehicles that want to be using that lane for different reasons. And so we realized that there was a phenomenon going on here that was common in these urban areas, but that hadn't really been systematically evaluated in terms of the effect on traffic flow related to delay and capacity, and also the effect on vehicle interactions. So some of our empirical observations, because there's been a lot more attention paid to blockages associated with bus stops, for example, is that freight deliveries are a little bit different from other types of blockages that are associated with bus stops or parallel parked vehicles. And that's that the locations of the freight deliveries are randomly distributed along the block. Typically, trucks will pull up right in front of the address they're trying to deliver to. So it could be right up by the intersection, or it could be somewhere mid-block. It's a random variable. The duration of these deliveries is typically much longer, certainly longer than the stop that a bus makes to load and unload passengers, or that a car makes when it's pulling up to parallel park into a parking space. On the short end of what we observed, we saw a couple of brief stops that took only a couple minutes, but often these vehicles would be stopped for 20 minutes or more. And so there's a lasting impact that this blockage and bottleneck has. And this impact is much longer than a typical traffic signal cycle. So whereas some of the other research that's been done to look at the effect of buses really tries to get into the nitty gritty of when during the signal cycle does the bus stop and was the light green or red or how many seconds. Um, a freight delivery is a longer duration of impact. And so we're sort of interested in what is that long term over the several signal cycles that it's occurring. What is that impact on traffic? The other thing we recognized is that there's a propensity of drivers to use the space in front of blocked vehicles, and it does depend on where along the block the delivery vehicle stopped and what the road conditions are. So what I mean by this is that if a truck makes a delivery and is blocking a lane of traffic, vehicles certainly have to get out of that lane to get around it, but they do tend to go back, switch back into that lane and fill up those lanes, especially if they're going to make a turn or if the signal is red and they want to use that as queue storage space. And so just writing off that lane as lost is not exactly right either. And then certainly this last point is that urban freight deliveries are not accounted for in signal timings. It's not something that's legal to be double parked. And so it's not something that goes into the design criteria or guidelines. But things are changing. We have technologies now that we could imagine could allow us to detect that these deliveries are happening, right? With image processing of video feeds, such as the one that I just showed, or perhaps if shippers were incentivized to communicate where they were making deliveries, we could maybe have some information about where these are happening, and potentially we can do something about them, right? We could either incentivize shippers to make deliveries in parts of the block that are having least impact on traffic, or we could adapt traffic signals to sort of account for the effect that they're having on the network. So the first part that I want to talk about a little bit here is an analytical model that we developed. And we started by looking at conventional traffic flow theory for an unblocked intersection. And here's a diagram of a two-lane, one-way street in an urban area with a traffic signal. And we assume that on such a street, when the light turns red, the vehicles queue up. And when the signal turns green, they can discharge through the intersection at the full saturation rate, the full capacity of that intersection. And they're otherwise unblocked. And in this type of a case, we get the conventional queuing process that we use to calculate the delays at intersections. And so on the left here, I have a diagram. This is a queuing diagram showing the cumulative arrival of vehicles at a constant rate in this case, so the simplest calculation. If they're arriving at rate Q, that's some general overall level of demand. And then we have a period of effective red time that nobody's getting through. That's C minus the green time. That's the signal cycle minus the green time. And then delays are accruing as those vehicles queue up. And once the signal turns green, they can discharge at the saturation rate. That's that steeper slope S for as long as the signal is green. And this implies the minimum amount of green time that's required to clear that queue. Right? So where the departing slope meets the arrival slope, that defines the minimum amount of time that the signal needs to be green to clear out the queue that had built up. So these are conventional calculations. You can find them in any of the traffic engineering texts, and it's what we use to calculate the delays at signals. When there's a blockage, we know that we don't necessarily get a full use of that saturation rate during the green. So what we looked at was sort of the nearest we could find to the conventional guidelines for how would you deal with a freight delivery. And there's currently nothing in the highway capacity manual to design for freight deliveries, but there are guidelines for dealing with bus stops. And the guidelines say that if a bus stop is within 250 feet of the intersection, that's 76 meters, you effectively lose that lane worth of capacity, right? So they say if it's closer than 250 feet, you just consider it blocked. If it's further than 250 feet, it's as if it doesn't exist. So it's this binary all or nothing type of model. And what that would look like in a situation like this on this street is that when that truck is making a delivery or that bus is making a stop, the vehicles can queue up only in one lane. And when the light turns green, they can only discharge at whatever capacity the flow rate, saturation rate, was able to get past the truck. And this gives a coarse approximation. It certainly would reduce the capacity of the roadway compared to what it would have been otherwise. And we can draw what the queuing diagram would look like in this case. Right? It would be a lower saturation rate for the signal cycles that are blocked. And so the delay calculations look really similar, except now we have this condition. If X, the location of the delivery, is less than 250 feet from the intersection, we use the blocked saturation rate, which results in greater delays. And if it's greater than 250 feet, use the previous unblocked calculation. It would be the no effect accounted for from the delivery. But we knew that this wasn't quite right. And this diagram shows what the actual vehicle operations would more likely look like. And if a freight vehicle is making a delivery at location X, distance from the intersection, we know that there is a bottleneck at the location of the truck, and vehicles cannot get past that point at greater than the capacity of that lane. But they could queue up using both of the lanes in front of the truck. And in fact, they seem to do this. So that when the light turns green, you can discharge the queue that's built up in front of the vehicle with a capacity of the 2 lanes. And then only after that queue's been cleared are you restricted to the capacity of what can get past the truck itself. So this is a finer model, a more detailed model. And it requires us to calculate based on the arriving flow, how long is the queue going to grow? So we can calculate the critical distance, call it X crit. That's the length of the queue if there was no truck present. And if the truck is closer than that, it means that the delivery is interacting with a queue of vehicles that's building up each signal cycle at the intersection. If the location is further away than the length of the queue, then it actually doesn't interact. It doesn't have any effect on the delay. And so when we calculate out the delay, we now have this new calculation that acknowledges the location of the blockage. And so the details of how I derive these formulas is not so important. You can look that up in the report if you're interested. But the way this queuing works is when the signal turns green, we discharge at the high rate up until we've served all the vehicles that were stored in the queue in front of the vehicle. So that's up to the distance X at the jam density K. K is the jam density. That's the density of vehicles per mile or per kilometer on the road when they're all lined up one after the other at the red signal. Once you've cleared out that queue in front of the truck, vehicles can only get through at the rate that they can get past that truck, and that's that lower rate that you see adding. So in a sense, the course model is giving the most pessimistic view of what the effect of the vehicle on traffic flow is. And this detailed model represents the subtlety, the idea that the location of the vehicle matters, and as you move the vehicle away, it will have an impact on delays. So we threw some numbers at this. These are some hypothetical numbers for a signal cycle that 50% of the time is effectively green. We imagine that we had an arrival rate and saturation rate through the intersection when both lanes can get through, and also a saturation rate associated with blockage. So maybe if the freight vehicle blocks half the road, then you get half the rate that vehicles can discharge. And we estimated some jam density. This was to throw some numbers to the problem. And what we get is a comparison of the average delay per vehicle that you would experience based on the location of the freight delivery. So the red line at the bottom, the unblocked baseline, is if there was no freight delivery at all, we'd expect this particular case to have an average delay per vehicle of 20 seconds per vehicle that approaches the signal. In the course model, if we use sort of the highway capacity manual's current nearest practice in terms of the way they handle bus stops, for example, we would say that you'd lose the entire lane for any vehicle that stopped closer than 76 meters from the intersection, and it would have no effect for vehicles that are further away. So you get this sort of step function that the delay per vehicle increases to 30 seconds per vehicle for any of the near stop locations, and it drops to negligible thereafter. But a more detailed model that accounts for the traffic interactions and the traffic dynamics looks messier to write out, but is no more difficult to solve in a computer or through a spreadsheet or some software. And it shows that the delay, the impact of the vehicle, of the delivery, decreases gradually as you move away from the intersection. So right at the stop bar, you do effectively lose the entire lane because everybody's got to get past that vehicle to get through the intersection. But as you move it back, you increase the amount of storage area in front of that vehicle. And so you have fewer and fewer vehicles that are impacted by that freight delivery. And then there's a critical distance. In this case, it happened to be at 100 feet, or 100 meters, I'm sorry, with these numbers. And that was the length of the queue when there was no freight delivery. So if the freight vehicle stops behind where the queue had last ended, then all that merging behavior happens in free-flowing traffic, and it's not impacting the queue storage or forcing queued vehicles to try to merge into each other. All right, so this is as far as we got with an analytical model. We knew there was something here that was a relationship that the location of the freight delivery mattered. And we wanted to explore this in a model that was accounted for more of the variability that you would see in the real world. And so for this, so moving away from an analytical theoretical model where everything's uniform and perfect, we decided to look at some a microsimulation. So I guess I had a couple insights here just from the analytical model. We knew that simply adapting the highway capacity manual methodology to freight vehicles gave this all or nothing approximation that didn't really fully capture the effective location. And we know that that effect diminishes as you increase with the distance from the intersection. And the proposed detailed model is really not that much more complicated to solve. It's a little more effort to derive, but not much more difficult to solve. And so that accounts for this effect. And what we wanted to see was if this was consistent with a pattern we would see in microsimulation. We tried to look at quantifying this with what we were observing in the videos, but there are so many confounding factors in a video that it was really impossible to isolate a single delivery effect, at least from 8th Avenue in New York. So we wanted to get at as well. Let's create a simulation environment where we can really systematically isolate the effect of the location of the vehicles, and we can place them at set distances from the intersection and look at their effect. So what we did was we used AimSun. AimSun is a microsimulation software, and we built a model, a section of 8th Avenue in New York, and gave it the lane configuration the same way it looks like on the street. And 8th Avenue is one way northbound, and this is between 36th and 37th Streets. And I guess we actually did also simulate the next intersection downstream so we could get the effective queue spillbacks in the case that mattered. And we loaded up this this model with traffic. In this screenshot, I guess there's only cars, but I'll show some videos in a moment. We loaded it with vehicle counts and heavy vehicle counts that were similar to what we identified in the videos of the street. We did try to simulate also pedestrian counts, but the number of pedestrians in Manhattan in this part were so great it overwhelmed the limit that our simulation package would track for pedestrian movements. And that's sort of a consequence of the heavy pedestrian volumes in New York. And so what we did was, rather than try to represent the individual pedestrian movements, we looked at adjusting the turning volumes, the capacity for turning, to reflect the presence of pedestrians. So we could watch in a video how many vehicles were typically able to make a right or left turn during a signal cycle. And those were impacted by the number of pedestrians that were crossing the street. So in the case that we had heavy pedestrian volumes, maybe without pedestrians, we could have gotten 15 or 20 vehicles making a right turn, but in reality, only 4 or 5 got through. So in that case, we sort of went into the parameter settings of the simulation and calibrated them to represent realistically the saturation rate that gets through the intersection on the green in the through direction and also for the turning movements. So when we do this, I have some videos here. This is one. You can see that the turning vehicles go excruciatingly slowly. That's to account for the effect of the pedestrians. And relatively light traffic volume. We can see the vehicles sort of filling in. We were able to run simulations with different volumes of traffic, very low volumes, much higher than what we actually observed. But we can capture with the simulation not only the delays, but also there's a representation of the vehicle interactions, right, based on the car following rules that the simulator has built in, and there are lane changes and things that are made because each vehicle is randomly assigned according to the origin destination paths a route from origin to a destination. So they pick their lane they need to be able to go through or turn right or left. And so we can quantify using the simulation what are the delays, the capacity, and the vehicle interactions when there are no deliveries being made, or in cases that a delivery is being made. And freight deliveries are not a built-in feature of AIMSUN, but you can define an incident and you can place it in any location that you want. So for example, when we wanted a freight delivery to be represented at the intersection location itself, we could draw a little red box here, right up at the intersection in that right lane. And this was a blockage that represented our simulation of a freight delivery. And so when we run the model, all the vehicles that end up in that lane are required to change lanes out of it. So you can see that now we only have 3 lanes of discharge capacity to get through the intersection, and anybody who was in that right lane had to change lanes to get out of it, and it impacted the entire queue, right? So anybody who queued behind it would have to change lanes into the other lane to get around the blockage. We could also move, we tried all kinds of different locations. So these little dashed lines at the bottom are sort of measurement to denote the different distances. That was something Aaron had added to help him visualize the locations. But we also tried mid-block locations, for example. And you can see that in this case, many of the vehicles will have to change lanes to get around the blockage, but they can queue up during the red signal using all 4 lanes. That when the signal turns green, they can discharge at the full capacity using all 4 lanes until they've used up that queue storage, and then anybody who gets past after that is restricted only by the capacity to get past the stopped vehicle. So I'm showing a video from X at 0 feet and X at 100 feet, but we tried increments of 25 feet, so lots of different points of comparison. And what we found was, from a large number of simulations, there is this declining pattern, just like we found with the analytical model. There's a declining pattern related to delay. And this was just based on, we ran the simulation, we did 20 iterations. With the baseline, those 20 iterations, there's random variation from cycle to cycle just because there's some fluctuations in the number of vehicles and the particular speeds that each vehicle wanted. But they hovered right around 14 seconds per vehicle. And the lines above and below are showing the 95% confidence interval of that mean. So based on those replications, those simulation runs, that's our sort of confidence interval of what's the mean average intersection delay with no freight delivery. And then you can see each of the other data points shown in purple is associated with a freight delivery at 0, 25, 50, 75, 100, 125, and so on feet from the intersection. And we did 20 simulation runs of each of those cases to build a confidence interval around them. And you can see that there's a statistically significant increase in delay associated with the deliveries that are close to the intersection. And as they move back, there's a diminishing effect until there's really not a statistically significant difference at all, right? So in this case, somewhere around 100 feet, it really doesn't have much impact at all. And from the video, that was the location that was upstream of the queue. So there wasn't any queue interactions, and so you don't really lose any capacity. There's not much effect on delay. So from an efficiency perspective, this implies that we'd be better off incentivizing freight deliveries, if they're going to have to double park, to at least do it far away from the intersection, as far upstream from the intersection as possible, so that they don't interact with the intersection flow itself. But this simulation also allows us to quantify all the vehicle trajectories that pass through the intersection or pass through that link. And when we do that, well, we can run those trajectories through an analysis to look at surrogate safety measures. So the thing about microsimulations is the vehicles never crash. And sometimes there's bugs in the software that allow a vehicle to visually look like it's driving right through the other, but you never get an accident or a collision because the car following rules will always override and they'll have some extreme braking or something. They're always assumed to follow the rules and be paying attention. But vehicle-to-vehicle conflicts can be quantified and they can be analyzed from these simulated trajectories. And so there's a surrogate safety assessment model that has been developed as a software tool by FHWA. And it analyzes the trajectories from simulation. I guess we could analyze any kind of documented trajectories, but you can export the trajectories of the vehicles from simulation, and it will categorize them based on the angle of the vehicle. So if the angle, based on this diagram, if the difference in angle of the vehicles leading the trailing vehicle is less than 30 degrees, for example, it's considered a rear end collision because one would basically be hitting the rear of another vehicle. If it's at an angle that's greater than 85 degrees, it's considered a crossing conflict, which could even be like a head-on collision, but with crossing paths. So it could be perpendicular or somehow head-on. And then if they're between 30 and 85, it's considered a lane change type of conflict because these are the types of angles that are associated with two vehicles that are going predominantly the same direction, but one's changing angle relative to the other. And how these get sort of categorized as conflicts has to do with thresholds related to various measures, like the time to collision. So the time to collision is a measure of the vectors of the two vehicles, comparing how long, if they continued at the same speed and direction, would it take for them to crash. Or another measure is the post-encroachment time. So it's how long does it take after one vehicle moves out away from a space for the second vehicle to occupy the same space. Okay, and so if these are very short, if the time to collision, meaning that an adjustment of vector, a turning maneuver or braking maneuver is required, or the post-encroachment time is very small, this indicates an increased likelihood of crash, right? That some probability in reality, people would make a mistake or there would be some increased likelihood of a collision of the type categorized before. The software also documents or quantifies the initial deceleration rate, the maximum deceleration rate, maximum speeds, and the speed differential between the vehicles. And one that is associated with the severity of the crashes is a calculation of the velocity change associated with a conflict. So what would be the difference between the initial and final speed? So if the vehicles are moving almost exactly the same speed, that would be different than if you have a stopped vehicle crashing with a moving vehicle. And so that gives a surrogate measure, not a direct measure of crash severity, but a surrogate measure of how severe crashes might be. So in a microsimulation, we would never observe the crashes directly, but we can count the number of conflicts. And the tool is designed to work with trajectory files from a number of commercial products. VisSim, I use AimSun in this case. Paramix is another one, and we also use it with Texas, another microsimulation tool. And a validation study that they cite, this is not my work, but they analyzed crash data from 83 intersections that they then modeled in microsimulation, and it suggested there's a strong correlation between conflicts and crashes, right? That the number of crashes per year could be estimated by this model, raising the rate of conflicts per hour up to this 1.4 factor and multiplied by 1.2. I think the R squared on this model was about 0.6, so it's not a perfect predictor, but there's certainly some correlation. The idea being that these surrogate measures give us an indication of the risk of crashes. So if we're measuring more conflicts in a certain environment, this would imply that there's a greater risk of crashes, that we would expect potentially greater crash numbers in those cases. So I did not actually, in this study, we didn't apply this conversion rate because I think there's so much tuning and calibration that would be sort of necessary to understand the particular details of conflicts related to urban freight deliveries and crashes around these locations. But we at least sort of work from the premise that conflicts are somehow related to crashes or related to crash risk. And the direct output, this is the visualization that's provided by SSAM. There is a tool, if you use VisSim as your microsimulation, it can directly load in the map and show the conflict locations right on the map. It's not so direct and easy on AimSun, so I didn't have a good way to make a visualization, but it plots on sort of two-dimensional axes the locations of all the conflicts that were detected from a simulation run. So we ran the simulations for each of the stop freight delivery locations many times, but this is one realization from one simulation run. And when there was no blockage, there are, in this top diagram here, there are a large number of these green circles. Those are rear end conflicts, and that's very common at a signalized intersection because when the signal turns red, vehicles come to a stop, and any vehicle that's coming to a stop behind another vehicle sort of runs the risk of a rear end collision. There's a conflict that requires the second driver to brake. And there's some number of lane changing conflicts, right? Those are these yellow squares, and they're sort of scattered around on the link. These we filtered only to look at the conflicts on the link where the freight delivery was occurring. So although the software will analyze all the conflicts everywhere on the network, we focused on these particular ones. When the delivery is made at location x equals 0, that's the second diagram here. I marked the approximate location of that delivery with an X. Then there are still a large number of rear-end conflicts because the vehicles are queuing up. But there's now an increased number of lane change conflicts. Right? And we can see that they're clustered right around the location of that freight delivery, right? Just upstream of that freight delivery. And a large number of lane changes, especially because the people in the far right lane are forced to change lanes out. It only shows up as a lane change conflict if they're interacting with another vehicle. So a lane change where there were no other vehicles on the road wouldn't appear as a conflict, but here because there were other vehicles in the queue, there's lots of sources of conflict. And then the last diagram down here at the bottom is when the delivery is at location 100 feet from the intersection. Still a number of rear-end conflicts at the intersection itself, but the lane change conflicts are all clustered right upstream of the freight delivery. Nothing really surprising here. You can all imagine that that's where the lane changes happen to be. But what this tool allowed us to do was to quantify not only where they were happening, but how many conflicts there were. So when we plot this out, we compared the number of rear-end conflicts per hour in cases where there was a freight delivery being made to baseline. And again, the red line here is the rear-end conflicts per hour when there was no freight delivery. We ran several realizations, so we had some random variation in the particular numbers of vehicles that were interacting. And we were able to build then a 95% confidence interval around that mean, right? So right around 100 conflicts per hour at this intersection under the normal operating conditions. And when the freight delivery vehicle is right at the stop bar, 0, we more than double that number of conflicts. But you can see that the number of conflicts decreases as you increase the distance where that delivery is made relative to the intersection. So as you move it back, fewer and fewer of these rear-end conflicts until the risk is really no different than it was in the baseline case. And that really seems to map directly to the delay effect, that the rear-end conflicts has a lot to do with the development of the queues. And if you remove the freight delivery from the queue interactions, then the rear-end conflicts in the queuing is just as it was before. The lane change conflicts also increased, actually even more substantially. So in the baseline case, there was about 20 conflicts per hour, lane change conflicts per hour, and that more than tripled when a freight delivery vehicle was put at the intersection. And it's particularly bad when the freight delivery vehicle was right at the stop bar because every vehicle that needed to change lanes out of that right lane was interacting with the queue. And so there was almost always a vehicle in the lane to the left that was creating a conflict for that vehicle-to-vehicle interaction. But in this case, the number of conflicts also diminishes, although not sort of the same exponential or curved way. It's sort of a more linear decline until the freight delivery is far enough upstream. It didn't seem to have much effect. So, in terms of a rear-end and lane change conflict, it appeared that the effect was similar to the effect on delays. And that's sort of encouraging because the things that you would want to do in terms of incentivizing freight delivery location or behavior would be the same for improving efficiency and improving safety. The third thing that we looked at related to safety was the surrogate measure of severity, looking at the maximum difference of speeds. And this didn't demonstrate much difference at all. It doesn't seem to matter where on the intersection or where on the link freight delivery is being made. The vehicles are more or less moving at the same speed everywhere on an urban network. And so the maximum difference of speeds was never very big because the vehicles can never really get going that fast on a dense urban street network. So the severity is maybe not impacted nearly as much as the number of conflicts and the risk of crashes, the frequency of crashes. So some insights here. The simulations confirm the effect that delays diminish gradually with the delivery location as you move it away from the intersection. So our analytical model seems to have a good descriptive capability for that phenomena. And these trajectories can be used with surrogate safety assessment model to quantify the vehicle-to-vehicle conflicts as a measure of safety. And so rear end and lane change conflicts both seem to diminish in the same way that delays did. And as I said, it really seemed to have a lot to do with whether or not the delivery vehicle was interacting with queues. But the max difference of speed was not significantly affected. It didn't appear that the severity of those crashes was necessarily changing. All right, the last piece that I have here is not as related to safety. We base this on the delay part, so I might go through it a little bit quicker unless you have questions, and we can go back. But this was the idea that we thought, well, maybe if we have a new representation of the delay accounting for the presence of delivery vehicles, perhaps we could re-optimize signals to account for that. And we wanted to figure out, was there room for improvement? Could we improve the efficiency of urban street networks by retiming these signals? So one of the things we know now is that urban freight deliveries certainly affect intersection capacity and delays. Currently, double parking is banned, and so as an illegal maneuver, it's not something that we designed for. It's generally considered something that shouldn't be happening in the first place. But the efforts to ticket for this or enforce it are not really changing behavior, and so it's a reality. And so the thinking is, what if these deliveries can be communicated or detected in real time? Is there something we can do with signals to account for this phenomena? So in an unblocked intersection, a common objective is to minimize the total intersection delay. Right? We can calculate the delay if we have two crossing streams, two one-way streets that are intersecting. We just sum up the total delay that all those vehicles experience. We want to minimize it, and we have some constraints. We have to provide a minimum amount of green time to keep the intersection undersaturated. We need a minimum amount of green time that pedestrians in the parallel crosswalks can get across the street. And in an urban network, it's typically important to keep the signal timings, the green times and the lost time, within a fixed cycle length that you can coordinate with other intersections in the network. And this type of problem is a convex optimization. It's an integer problem, but it's a convex problem with linear constraints, and it can be solved relatively efficiently. The signal optimization with blocked intersections is more complicated because we have two different cases. We have the case that the blockage is close enough to the intersection that it interacts with the queue, or that it's far enough away that it doesn't interact with the queue, and that triggers two different calculations of the delay depending on where you are. And the challenge is that as you change the green times and the red times, the signal timings, you can change which criteria you're on. So it's not something that you can just look at in advance and say, oh yeah, we're in case one or case two. It depends on the signal timings as you're optimizing them. And so we had to define this in terms of a y, an integer variable. This y term that is sort of selects the case. It's y is 1 if the truck is blocking part of the queue and there's an interaction that has to be accounted for. And it's 0 if it's far enough that upstream that it doesn't interact. And so we have the constraints defined in such a way that it selects the right constraints to define the problem correctly. We still have minimum green times that are required to keep the intersection undersaturated, and minimum green times for pedestrians to cross. We try to maintain the cycle lane. And so, the details of this, you could refer to the paper or the report if you're interested. But what this comes down to is we can implement this. It's actually not that hard of a problem to solve. It's a convex optimization with mixed integer constraints, but the bilinearity in this, sort of as a computational detail, can be approximated with a convex continuous function, and it's not so difficult to solve because there's only this one integer that's 0 or 1, and so just check it either way and solve accordingly. So we implemented this at this hypothetical intersection. This is the one that we looked at with the analytical model in the beginning. So, well, what if we have this intersection and a freight vehicle makes a stop, and it's going to stop for several signal cycles? What would we do with the signal timing? And so we looked at what's the effect on delay for different levels of arriving vehicle flow. So if there are 400 vehicles per hour arriving or 600 vehicles per hour arriving, the dashed black line here is the baseline delay, average delay per vehicle. That's what you'd have with no blockage. If there's a blockage there and you didn't change the signal timings at all, you get the blue line. So we know that the closer that that vehicle is to the intersection, the more effect it has on increasing delays. If you re-optimize the signals, accounting for its presence, you can't eliminate the delay increase entirely, but you can diminish it. You get this red line. So that's from the re-time signals. Okay, that's an improvement. It's something something that can be accomplished, but maybe not such a big deal. Maybe not worth all the effort. But when the arriving demands get higher, you can end up in a situation where an intersection that was undersaturated in normal conditions was able to serve all the vehicles that arrive and were in the queue during normal conditions. When the vehicle is blocking part of the lane, creates an oversaturated condition. You're not able to get everybody through. And so this blue line here, it stops. It actually is undefined for values of x less than 130 meters. And that means that it's oversaturated in those conditions. So if a vehicle is parked too close to the intersection in this case, the queue is going to build up and not everybody's going to get through, which means that in subsequent cycles, you can get even more vehicles built up and even more vehicles built up. And this is actually really damaging in an urban environment because that queue is going to spill back and block other intersections. And this is what contributes to gridlock. So anything you can do to keep an urban intersection undersaturated is going to act to prevent gridlock conditions. So re-optimizing the signals doesn't necessarily give you huge delay reductions for those cases that were covered by the dark blue line, but it does provide a much wider range of conditions where you can keep the intersection undersaturated. Not all conditions, but there are locations, from about 40 or 50 meters to 130 meters where double parked delivery would have created oversaturation, but when you re-optimize the signals, it's able to accommodate the flows. And we can also look at the effect, just sort of turning this around. If we fix the location of the blockage and then just quantify the arriving volume, the points where the lines stop represent the capacity of the intersection. So by when a vehicle stops to make a delivery, it reduces the capacity of the intersection, and by re-optimizing signals, you can increase that capacity somewhat. And then a final way that we looked at this was to try to compare the delays, the average delay per vehicle, across combinations of arriving demands. So supposing we had a primary approach and a secondary approach, maybe they don't have symmetric arriving demands, then any combination, you could optimize the signals and see what the average delay would be. And in an unblocked intersection, this is the set of values you would get, right? So anywhere that's shaded with a color here is a feasible set of demands that's within the capacity of the intersection. Anywhere that's white is over capacity. It's oversaturated. Can't be served. And so you can see that the sort of largest delay is when you have a balanced combination. If you're really lopsided, you can give a lot more green time to one approach than the other. Well, what happens when you impose a blocked vehicle is you lose, if you don't change the signal timings, you lose a lot of area. There's a whole range of combinations of demands that are no longer feasible. So it's not only that the delays are bigger, it's that they can grow every cycle, every subsequent cycle, they grow and grow and grow. As the delays get longer, or as the queues get longer, you're adding more delay, but you're also adding more of these harmful vehicle interactions. When you re-optimize the signal, you can regain some of what was lost. So this just shows sort of the opportunity to serve demand pairs on the primary and secondary approach that could not be served before. And so some insights from this is that because the freight deliveries typically last for several signal cycles, their impacts have lasting consequences on the capacity. So whereas a bus or even a parallel parking car has an impact for a few seconds or a minute, a freight delivery may have impact for 20 minutes or more. And signals that are re-optimized for these, they can reduce delays a little bit. That's not really what we get excited about, but that you can maintain under saturated conditions allows you to clear these queues up, and clearing up the queues is going to reduce vehicle interactions on the roadway as well. So that's a summary of the analysis we did, sort of looking at the issues related to freight deliveries, the idea that they've been recognized as a problem but not systematically studied, and that we can quantify their effect on delays, capacity, and safety, at least using surrogate measures, using these tools, either analytical models or simulation or both. And I think the insights for policies are that if this is not something that can be banned necessarily, maybe incentives to drivers to make their deliveries in the middle of the block as opposed to right at intersections would be worthwhile. Maybe the tickets could have a higher penalty when the blockage is right at the stop bar, right at the intersection where we know it has the greatest damage, versus mid-block where it's has the least impact. So I'm happy to answer any questions. I don't know if we use the microphone for this or if you want to type them into the chat box, but I'm happy to answer questions or field any other thoughts.
Thank you, Eric. Yeah, we usually type the questions into the chat box, so if anyone does have questions, feel free to type it in there. Um, Interesting work though, and I can see how these freight deliveries would be a problem in urban environments. Have you spoken to any like DOT members about incentivizing parking mid-block or further away from the intersection? And if so, what are their initial thoughts on it? Obviously, it's a problem, and the tickets aren't necessarily working, but you necessarily don't want to, like you said, you don't really want to plan for people parking illegally.
Yeah, until recently, freight was kind of not even considered in urban transportation planning. A lot of the transportation modeling in urban areas is really focused on passengers, and so it wasn't really even on the radar. And one of the challenges is there's not very much data actually about what's being delivered and where. Um, Maybe that's surprising to people, but there are not really records of how many trucks are around or where they're going unless you go out and survey them. And they're less likely to share a lot of this information because a lot of the delivery companies are private companies that's proprietary information what they're carrying, and they're not as willing to fill out surveys about this stuff. I have talked to some people in Massachusetts. I've talked to people in Seattle. There's certainly awareness that this is an issue. I think nobody is eager to rewrite their code to allow double parking. I think there's sort of hesitation to change the policies on this, but there's recognition that what they're currently doing isn't working. And I think the most experimentation with this has been in New York City, where there's been a lot of these experiments with off-hour delivery programs. And the challenge that they have in New York with off-hour delivery programs is just that they're expensive. And that in order to get people to change the schedule of when they go, to make deliveries in times of day when there's not very big queues on the street, so it doesn't matter where you stop, you have to subsidize the businesses several thousands of dollars, and it just ends up being very costly. So one of the things that this could be used for could also be just to calculate if we can quantify the impacts or the social cost of these freight deliveries during peak hours. That could help judge, what is the right amount of incentive and how much is worthwhile. So it may not be that we end up allowing double parking, but maybe we can target the right magnitude of incentive.
Very interesting. Thank you. Well, it doesn't look like there is any questions, but you do have your email up there. So if anyone does have any follow-up questions, they can shoot you an email. Thanks again for the presentation, Eric, and thank you everyone for joining.
Thank you very much.
And so this will be up online within the next couple of days. You can send me or Eric a question if you have any, or send me an email if you have any questions about it. And I will talk to you later, Eric. Thank you again.
All right. Thank you very much. I appreciate it.